Hi everyone, welcome back. We're going to look today at some rearrangement of some useful equations that we're going to be using in our study of gravitation and motion. So in the West Australian curriculum, this is what you're greeted with at the start of the syllabus, a whole host of different equations, which might at first seem like they're all unrelated. What this little video is going to try and illustrate is that they're not related. In fact, they're all pretty much the same sort of an equation. So let's look at the first three that I have at the top of the screen. Now, if we look at the first equation, which is the relationship which Newton came up with, the gravitational attraction force between two objects at a distance, and if we compare that to the second equation, which is the equation for the weight force, and we say that, well, that force is the same force anyway, so let's just make that equation to be the same equation. So we've got that the force of gravitational attraction is equivalent to the weight force. So those two values, two equations are the same equation essentially. If we consider Newton's laws and look at his second law written in mathematical terms, it's F equals ma. And if we look at the equation directly above that, that means that g is a, and actually the symbol g stands for the acceleration due to gravity. So therefore, when we rearrange it, we can get the third equation, which is that g equals F on m. Now, if we look at what else that is equivalent to, which is the large G m on r squared, we see that that thing there is also equivalent to the acceleration due to gravity. But where do we get that value from? Let's go back to the first equation and have a look at it. So when we look at the first equation, if we rearrange it and take one of the values from mass out to the front, we see that the second part of that equation is the g m on r squared, which is the one we were looking at originally. So that's really saying that that value is equivalent to an acceleration. And when we look at the second equation, which is F equals mg, we can replace the big G m1 on r squared with just g, the acceleration due to gravity. And we can see that they're essentially the same thing. Okay, let's now look at a few of the other equations on that sheet. We've got potential energy equals mgh, we've got the work equals force times displacement, we've got work done equals the change in energy, and we've got kinetic energy equals half mv squared. So there's a few terms in there. Now we define work as being done when the energy of a system changes. We also can define work as being done when a force moves an object through a distance. So once we've got those definitions and we look at the two equations above, we also know that the weight force equals mg. So once we've got them, we can now see a few things. The force of weight, if we say that's equivalent to the force that's doing the work, and if we look at what mg is, and we can see that appears in the potential energy equation, and then we look at the potential energy equation and the work equation, we see that the change in height, that is a displacement. We actually see that those two equations there are essentially the same thing stated just slightly differently. So instead of mg, we can replace that with force. Instead of delta H, we can replace that with displacement, and those two equations are the same. And in fact, it says on the third equation on that list there that work is a change in energy. The fourth equation, though, looks a little bit different. So how can we explain where that one comes about? Let's just imagine that an object is falling, and if it falls, the gravitational potential energy that it has is now going to be converted into an energy of movement, a kinetic energy. The law of conservation of energy says that whatever energy is lost from potential energy will be gained as kinetic energy. Okay, let's go back to some Newtonian equations, not relativistic, but rectilinear motion equations. We've got v squared equals u squared plus 2as, a stock standard sort of an equation where v represents the final velocity, u is initial velocity, a is acceleration, and s is displacement. If we rearrange that equation, we get that 2as equals v squared take u squared. And just rewrite that now as 2as is the change in velocity squared. We can then divide both sides by 2 and get as is change in velocity squared on 2, and just rewrite that as as equals the change in half of the velocity squared. Now, because it's an equation, whatever we do on one side, if we do the same thing on the other side, it will still be an equation. So let's multiply both sides by mass. When we do that, we get that MAS equals delta half mv squared. Now MAS, when you look at the equations at the top, the potential energy is mgh, which is MAS, because A is equivalent to G and S is equivalent to H. So we can replace that with work. MAS can be replaced with work. So now we have work equals delta half mv squared. And from the third equation up there, we know that work is the change in energy. So that means that the change in energy is the change in half mv squared. And that means that the kinetic energy is half mv squared. So what we've done there is just shown that all the equations on that first part of the syllabus for our physics course, that looks like there's a lot of them, and it looks like they're all unrelated, but what we have done is we've shown that there's a relationship between them all. So I'd encourage you, when you encounter new equations in your course, look for relationships between that equation and something you already know, because invariably they're just restatements of things you already know.